So if there are no other technical issues to discuss, I would like to start with the first theoretical topic of this school, which will be an introduction to MPC, because we have to have some common ground from which we can start implementing optimization-based controllers. And I hope, and I'm pretty much sure, that most of the persons in the audience are already familiar with the concept of model predictive control. Nevertheless, I will provide a concise introduction into the topic such that we all know what we are talking about. And I will also try to provide maybe a different perspective on how industries view model predictive control and what is important for them when it comes to practical implementation of these optimization-based strategies. So if you were to sell MPC to somebody, of course you have to have a clear and convincing message to sell the people on. And my message for today would be that model predictive control is a safe and more profitable control strategy compared to existing approaches. I would claim that it's more safe because it explicitly tackles process constraints directly in the control design procedure, as compared to some patches or some hacks on top of existing strategies like anti-wind abyss for the PI controllers and some gain scheduling rules and stuff like that. In model predictive control, the constraints are first-class citizens. They are not an afterthought, but it is something that we incorporate into the control design procedure from the very early stages. And I would claim that it's a more profitable approach to control because it includes an optimization objective which can account for plant performance, like minimize the fuel consumption, maximize concentrations of the product, these kind of things. Okay? And actually, the process industries, nowadays, they don't need to be sold on the idea. They are very well known that if we would like to approach a good control for large industrial plants where money plays the primary role, the plant operators and owners, they are already sold on the idea. So they do know that MPC brings certain benefits that are of interest to them. However, what I would like to say is why MPC actually achieves this and what is the main competitor to model predictive control. It's not so much other control strategies, it's the plant operators. Because the plant operators, at the end of the day, they are responsible for a safe and profitable operation of the plant. And it is actually very frequent situations that the plant operators, they simply either switch back to existing control strategies or they even apply manual control just to be safe. Okay? Safety, especially in process industries, that plays the primary role. So what the typical operator tries to do is he tries to optimize performance, but he also tries to stay away from the constraints because he doesn't know what will happen, and maybe there is some disturbance that will hit him outside of the constraint set, which would be a disaster for the plant. By the way, just 1 day downtime of a medium-sized petrochemical plant is worth 400,000 euros. Okay, so if there is something which goes wrong, this has severe monetary consequences. So that's why typical operators, and also here you can count in the existing control strategies, they try to be conservative. On the other hand, we know that model predictive control, and by the way, in the industries, they always invent fancy name for standard things. So in the industries, they don't call it model predictive control, but they call it advanced process control, but it's the same thing. Okay, so they use the APC abbreviation, but it's model predictive control under the hood. So we know that model predictive control, being aware of the constraints, it can really push the performance of the plant closer to the constraints where we can maximize the profit. At least that's what the theory says would be the main benefit of model predictive control. This better performance subject to improved safety. What I would want to share with you is the following graph, which was taken from an overview paper by Ian Craig. And what it shows is what the MPC suppliers, so basically us, who develop these kind of techniques, what kind of arguments we use to sell MPC to somebody. That would be the light bars here, and the dark bars are the response of the users of MPC, so this would be the plant operators, how much they value individual improvements. Okay? And what I want to say here and to point out are these three categories. So we all know, or at least hope, that model predictive control will improve energy consumption. It will reduce it because that's what we account for in the objective function, right? And we always sell MPC based on this premise that it's a better control when it comes to energy consumption. And you can see that something like 65% of the suppliers of model predictive control, they use exactly this argument when they want to sell their technology to the plant operators. However, from the plant operators' point of view, it's only 45% of them who see this as the main benefit why they buy this technology. So what I want to say here is there is discrepancy between how we advertise certain control strategies and how they are perceived. And I believe there is quite a lot we can learn here, not on the technological side, how MPC works under the hood, but how to commercialize the approaches that we develop. Because one of the objectives of the Tempo network at large is to provide training, not just in the technical aspects of, say, embedded optimization, but also when it comes to entrepreneurship and these kind of things. So you can take this slide as the only one that I have there, which diverts from a complete technological description and just shows that sometimes we are overselling on certain aspects and sometimes we are underselling. The other one we are heavily overselling is the increased yield of more valuable products, which basically means we say in MPC we can maximize the, say, the purity of the products and these kind of things, which is just another side of the same coin of energy consumption. So these two basically relate to the accounting for the economic performance of the plant in the objective function. And the third one is kind of similar because, again, it relates to the quality of the production. So this shows that on these three we are overselling. But apparently we have lots to learn from plant operators. So one of the messages which I will not put explicitly is, before we even start developing some control strategies, we should learn what our users are, what are their needs, and what are the control aspects that they care about. And these bars here show that for them it's process stability improvement, which is a very valuable aspect of the operation of a particular control strategy. So what this means is that despite the fluctuations of the input flows, the control performance can level them out. So this is basically about disturbance rejection, of course, again, subject to constraints and so on. Apparently, a stable production is better than some marginal increase in the, say, the overall yield, if that overall yield is fluctuating too much. So in the process industries, they value steady behavior over maybe a little bit increased but fluctuating production. The other aspects where we are kind of underselling is, for instance, downtime reduction. So this might, for instance, account for retuning of the controllers. This might account for the MPC in nature being multivariable control. So recently we had a project at with the Slovak refinery here, where the problem basically was that they had a stuck valve. And they had 3 tanks through which the distilled oil was processed. And basically, because of that stuck valve, they got huge oscillations in the bottom tank. And this was undesirable because that's where the oil stays for the most time, and fluctuations are simply a big problem. So of course, the first question which we asked them was, okay, so just replace the valve and the problem goes away, right? And they said, exactly this argument, we could do that in one day if you kind of cover the cost of 400,000 of a day downtime. Okay? Of course, they have huge redundancy in the control system that can be utilized just by not by the standard controllers like PI controllers, where you close the loop based on one measurement, you control one safe valve. in MPC, MPC can recognize this kind of redundancy and adjust the remaining control inputs just to compensate maybe for a failure in some other actuator. And this is a factor which is apparently well valued by the plant operators, and it might add to the value of the product that we are developing for them. Okay? So the bottom line is, I will continue with selling MPC on the premise of being safe control, that it respects constraints. It's economically optimal control. Of course, we can debate optimal. I will say it's optimal with respect to a given cost function. But apparently, there are other factors on which you can sell these technologies on. And I will leave this completely up to you. I will be your customer on Friday when I will be listening to your presentation. So you will be the ones who will convince me. You can pick kind of one of these discrepancies, maybe focus on like more stable behavior of the controller rather than on transients and these kind of things. Okay? And actually, continuing on this, when I started working on MPC some 15 years ago, I was very much sold on the idea. It looked so interesting, and I saw that the potential improvement is huge. Actually, it turns out that, again, if we talk about model predictive control in the process industries, which is not all the application areas, and it's kind of the exact opposite of what the Tempo network tries to achieve. In the spirit of the Tempo network, we try to implement model predictive control for tiny plants, okay? Not those large industrial complexes, but still the average reduction of the operating costs is, at least at the first glance, not that huge. It's 2 to 6%. When I was young, I was expecting something like 50, 80% improvement. It turns out what the plant operators already have available is already very good. So they have basically tens of years of experience. They have a spider web of PI rules connected with lookup tables. Basically, if you look at their existing solutions nowadays, they are trying just to heuristically mimic what the model predictive control strategy is doing, but they are doing it with very simple building blocks. So it is also nowadays quite difficult to find some large amount of improvement, but there is improvement nevertheless. Each of these percentage here, that translates to millions of dollars, for instance, for the petrochemical industries. Okay? So there is still room. Of course, everything has its price. So if you ever were to work for some large automation company, and there is, of course, the question how much you should charge for your solution, then the typical rule is that the plant operator should get somewhere between 3 to 24 months of return rate of the investment. So these are actually very expensive solutions that the automation industry is providing, but nevertheless it pays out for the plant operators. So just to wrap up this historical and industrial excursion, what I want to say is that nowadays, those people who have money, they already do know about MPC, so it's not difficult to convince them to jump on the ship. We just have to find good arguments for them and not to sell something which they don't care too much about, and maybe using that graph identify points which might make the selling a little bit easier. And then we come back to theory. So we all know what model predictive control about is, right? Model predictive control is an optimization-based control strategy where we take the plant measurements and the references and the cost function and the constraints into account to find the optimal control inputs for the plants. So in a way, it does not differ from existing control strategies which are based, say, on linear feedback loop. But what I want to say is that conventional control is basically reactive control. It's like driving just by looking on the side, through the side window and just reacting to your current situation. While model predictive control is, of course, looking forward, taking the outlook of the future reference trajectory into account, maybe taking some time-varying nature of the constraints into account, and so on. And then it comes to optimization, right? So what we do in model predictive control, and here, by the way, I should say that this is, of course, maybe too familiar for most of you, but I was asked by Eric that at the end of the day, you need to know how the quadratic programming formulation of MPC looks like, such that you can start implementing it on FPGA, and the same applies then for Arduinos. So what I'm doing right now is I'm heading towards that QP formulation. Okay. So we know that in model predictive control, what we do is that we take the current measurements into account. We consider the process model to predict the future evolution of the plant. And we have constraints that we have to respect, and we optimize over some finite prediction horizon the sequence of control inputs which will bring the predicted planned evolution as close as possible to some reference trajectories. Of course, there are other concepts like economic MPC, where we forget about set point tracking and we directly use, say, maximization of the planned profit and these kind of things into account. But I would say that let's stick with the traditional objective of MPC, which is set point tracking. And then once we have this sequence of optimal control inputs decided by optimization, then in the spirit of the receding horizon implementation, we only isolate the first element of this optimal input sequence. We apply it to the plant. The plant will reward us by new measurements, which in a better case are quite consistent with our predictions. In practical terms, because of noise, model plan mismatch, and these kind of inconvenient things, the state estimate will differ from what we predicted. But nevertheless, we take the new estimate or the new measurements into account. We shift the prediction horizon one step into the future, and we repeat the whole procedure. So this is called the receding horizon implementation, where we solve a given optimal control problem at every sampling instant to decide what the sequence of optimal control inputs should be, and then always taking the first step, applying it to the plant. And this is basically what introduces feedback into the control action. So now it's mostly about this optimization problem that we have to solve. Because in the conventional receding horizon implementation, we need to repeat the optimization at every sampling instant. Of course, there are, I would say, theoretical algorithms which say that if your controlled plant is open loop stable, for instance, then we do not need to repeat the optimization at every sampling instant. We can let the plant evolve in an open loop fashion for a limited amount of time. But I would say that these are fairly theoretical development and not finding their way yet into practical MPC products. So I will stick with the conventional notion of receding horizon control, of having to repeat the optimization at every time step. So it's about the optimization problem, the optimal control problem, I should say, that we need to solve at every sampling instant. And it takes fairly general form. So we have the cost function, which consists of some terminal penalty term, and it has some stage cost accumulated over the prediction horizon. And then we have a bunch of constraints that are imposed over the prediction horizon. So first of all, we have equality constraints, which determine how the plant reacts to a choice of control inputs. So this function f here would be the process model. Then we have some path constraints, which restrict the selection of the control inputs, such that they do not lead to violation of input and state constraints. We have some terminal constraint, and here this terminal constraint together with the terminal penalty, these are just theoretical additions to guarantee recursive feasibility and these kind of issues. But another very important constraint is that we have somehow to initialize the problem. And for the initialization, we would love to use the direct state measurements, but I mean, this school is about reality, right? About the implementation of these strategies. In reality, we very seldomly have the full state measurements available, so we have to resort to state estimation, which is a problem on its own. Okay? It would deserve not just a separate summer school, but maybe a separate Tempo European project just on this topic. For us, we will just assume we have a consistent state estimate available, and we will not care too much about how to obtain that. And in theory, all the components of this optimal control problem, they can either be nonlinear or non-convex when it comes to sets, right? And this is even what people would love to have. I mean, the holy grail of MPC is to do model predictive control in continuous time, so not to resort to time discretization as we do here, because we are only considering discrete time instances. So do MPC in continuous time, do it with nonlinear prediction models, and maybe even use some non-convex cost function like the people in economic model predictive control do. However, practical implementation of model predictive control requires making certain concessions, such that we are, at the end of the day, able to implement and solve this optimal control problem, not just on some hardware, but on a hardware which we are told to use. And the concessions that we always make are that we restrict ourselves to convex cost functions, which basically means that this stage cost here and the terminal penalty are either convex quadratic functions or they are composed of weighted 1 and infinity norms. The prediction models, we deliberately restrict ourselves to linear prediction models. In practice, then, what they do is, from time to time, they perform some step changes to identify a better model, because in MPC, since we need to solve the optimization problem repeatedly anyhow, nothing prohibits us to change particular components of this optimal control problem from run to run. So if we have better, say, parameter estimate of our linear system, fine, we can use an updated model. So linear models are fine, at least in some limiting range of the operating conditions. And last but not least, we assume that these constraint sets here are polyhedra. And under these conditions, we end up with a convex optimization problem that we at least have a hope of solving on a particular hardware. And actually, this is where things start to get interesting. Once you start talking about implementation, half of the academicians in the room, they probably stand up and leave, because they say, these are just implementation details. Let my student handle that, okay? The whole premise of this school is, it's actually the other way around. We should think first about the hardware implementation, because then it might very well impose restrictions on the type of optimal control problems that we are allowed to formulate in the first place. So if you start even maybe you end up with a quadratic program, and then you say, it's fine. I mean, everybody will be able to implement it. Maybe your hardware does not allow to implement these kind of optimization strategies. So I'm going to argue that execution of any control strategies requires 3 types of resources. The first one is time. Okay? So the time basically translates to how much processing power your CPU has to implement any control strategy. And if you think in terms of notebooks and PCs, I mean, we have teraflops. I mean, we have graphical cards, so we can do really teraflop operations and so on. Most of the process hardware, again, in the process industries, and your mileage may vary here because there are people here from different areas, some of them implementing model predictive control on mobile robots, some of them doing like flight things and so on. But some of you, they might encounter the need of implementing MPC on some ancient hardware. And that ancient hardware is really ancient. We are talking CPUs from 1980s. Most of you weren't probably born on that. You were born later than that. So time is an important factor. And here I would say everybody knows that time is important, because everybody knows that we have to complete the optimization inside of one sampling time. Good that Eric is not here. He would immediately jump in and say, but there are theoretical approaches which say we can sometimes violate that. I'm not going to dwell into the theoretical discussion. I'm just saying that the classical receding horizon implementation pretty much relies on repeating the optimization at each sampling time, which means our computational time is bounded by the duration of the sampling time, right? And everybody's known about this. But then people tend to forget other two important aspects. The second one being space. Because at the end of the day, your optimization algorithm will take form of some kind of a program, right? So you first code it maybe in the C language, and then you compile. And then you say, so I just take the compiled program and I just upload it to the target device. But what if the target device doesn't have enough memory? I mean, we are screwed, basically. So space is equally, if not even more important than time, and it's very often neglected. And the third aspect, and that's the reason why all of you are here, is that it's not just about time and space, it's about the type of hardware we intend to run these algorithms on. Because each of them has severe restrictions. In the second half of this lecture day, we will talk about programmable logic controllers, which are programmed basically by the assembly language. So like putting instructions like add two numbers together, and you can always just add two numbers and not three of them. If you want to add three numbers, you have to split it into two instructions, these kind of things. So once you factor in the complexity of the implementation platform, what kind of code it allows you to write, it might be again a decisive factor which influences the type of the optimization problems that we are even able to tackle. And some more details about these three aspects. So sometimes it actually turns out that at time, which everybody is aware of, is the kind of the critical factor, is the least critical of these three aspects. Because we can sometimes violate the premise of having completed by the duration of the sampling time. However, in general, if we do that, we might lose optimality. I mean, that might not be the end of the world. In the worst ways, we might lose constraint satisfaction. In the worst case, instability. So it is not advised to violate these time constraints, but as I said, they are really not the toughest one from these three. It's really about space and the platform, because unless we can fit our code into the control platform, we cannot implement the control in the first place, right? So what sense does it make to have an ultra-fast model predictive control strategy which terminates in 10 nanoseconds when you need a code which is 1 megabyte in your device on which you run it has 8 kilobytes of memory? Okay? So space is often neglected. It's actually hilarious how much neglected it is. I mean, just look at, for instance, recently there was the IFAC World Congress. Just look in any paper which deals with MPC implementation and look for some figures on how much space does the control strategy require to be implemented. Well, I would claim 99% of papers don't mention this at all. Okay? They just kind of hope that it will fit, okay? But there is no guarantee it will. And the third one is, the platform really is about something that if you start your application from the ground up and you are kind of in charge of the control strategy, then you can usually choose the hardware such that it can accommodate the control strategy that you are developing. But sometimes, and I would argue that very often, the hardware is imposed on the control engineer, and he has to tailor the control algorithm to the specific hardware. And this is exactly what the first topic of today, implementation on programmable logic controllers, will be. I will try to communicate to you how big these limitations on the platform are, and maybe it will give you a very different perspective how we approach control in general. But nevertheless, it's those three aspects. And as I said, they are very often neglected. In a better case, the time factor is kind of factored in, but that's it. Okay? So it almost occurs to me, and I'm counting myself also among these kind of things. So when we develop a new strategy, we design it, we test it on simulations, we write a paper on how good the performance is, and then we say, that's it, we have done our part, right? And then we just pretend that everybody will use the same hardware, but that's obviously not a reasonable assumption. Well, the more practical workflow or approach to designing any control strategy, not just the optimization-based controllers, would be to start from the very beginning by figuring out what the available resources are. And again, there are three types of resources: time, space, and the platform on which we run that. Okay? So we figure out, maybe the hardware is imposed on us, so we figure out what the limitations are. Then the next realization that we have to make is, and we, at least in the MPC community, we always tend to be selfish and we think it's all about the control algorithm. In practice, the control part is a tiny little bit of the overall puzzle, because in that duration of one sampling time and inside of all your available memory, the control strategy has to accommodate for other factors like signal filtering, state estimation, quantization effects due to analog to digital and digital to analog conversion. I mean, this can completely destroy the performance of any control algorithm. Things like diagnostic fault detection, data logging, these are kind of software modules which have to run on the same hardware. So it turns out that even if somebody tells you you have your CPU can manage a sampling time of, say, 100 milliseconds, maybe for your control algorithm and it's just 10 milliseconds allocated for the control task, and the rest has to be reserved for all these supporting routines. So this is also something we have to be really careful about, and not to be selfish about the hardware on which we will run. But nevertheless, we come to this realization, and only after we know, switch it off please. Only after we know what the limits are, then we can start designing tailored control strategies. So this whole course would be exactly about how to tailor optimization-based control design to specific control platforms like PLCs, FPGAs, and the Arduino microprocessors. And then you come to the final disappointment of the day, which is, again, if you just talk about process industries, then the operators might very well just switch off your controller completely, because it does strange things. I mean, strange according to their definition can mean pretty much anything. Basically, even going tighter to the constraints where you get better optimality, it's scary for the operator, so they just switch it off. Okay? But anyhow, it's all these things that we have to factor in directly at the very beginning design phase of any control strategy, and they are even of more importance when it comes to optimization-based control as MPC. So as I said, if we ever have to have a hope of running model predictive control in an embedded arrangement, we have to make concessions. So here we are going, and from this time on, we are going to focus just on the standard QP, meaning quadratic programming-based formulation of model predictive control, which means that we have a ideally strictly convex cost function, which is composed of weighted square terms that penalize the deviation of the state from the origin and the deviation of the input from the origin, and we have also some terminal penalty. And by the way, probably it's shouldn't even be said, but I will just for safety say that, of course, we are looking at linear models that are linearized around some steady state. So going to zero with this cost function, because obviously a minimum of a quadratic function is at zero, it does not mean that your plan has to kind of freeze when the state is a temperature, right? It just means that it converges to the linearization point or to your steady state. So we are looking at the regulation type of a cost function, which basically rejects any disturbances that there might be in the plant. We are going to consider a linear prediction model, say time invariant, to keep things simple. Then we have polyhedral state input constraints and the constraint on the final predicted state. And we have the initial condition for our optimization problem. And yeah.
Polyhedral constraint, does it mean it's a set of linear constraints?
Exactly, exactly. Yeah, so all these constraints, they are just pre-multiplied by some constant matrix, and we have a constant vector here, so it's just a set of linear inequalities. And a couple of the standard technical assumptions would be that the penalty matrices, they are strictly positive definite as to obtain a strictly convex cost function. And these polyhedral sets here, they contain the origin in their interior, which basically means that the right-hand side here has to be greater than or equal to zero. Well, better greater than, because then we have the origin in the strict interior of those sets. These are just technical assumptions which guarantee that there might even exist a solution to this optimization problem. Okay? What is important for us is how do we solve these optimal control problems? That's question number one. And question number two is how do we solve it on a particular hardware, taking into account the time, space, and platform limitations that we might have. And again, most of you are already familiar that there are basically two avenues we can take. We can apply what I called implicit or online optimization, which is the conventional approach, which basically says that whenever a new initial condition arrives at the next sampling instant, we just formulate this optimal control problem as some kind of standard optimization problem, say a quadratic program, and we solve it to obtain the sequence of optimal control inputs. And then when a new initial condition comes, we solve a new problem, and so on and so forth. So this would be this implicit or online optimization. The other avenue is to do the optimization offline and find an analytical solution to this optimization problem as a function of this initial condition. So kind of have the solution pre-computed and only implement the pre-computed solution. And I will go into details later on. But before we show how do we solve these problems, we first must translate them into one of these standard forms that we can treat, right? And usually what we aim at is translating these kind of optimal control problems into quadratic programs of this form. Okay? So we have, again, a strictly convex cost function of the optimization variables, and we have just inequality and maybe equality constraints. Okay? So what I'm going to do now is, again, a brief overview of how do we get from the optimal control problem all the way to the quadratic program. Because it turns out there are, again, at least two options. There is the so-called sparse approach, which is basically all about keeping the structure of the problem to be potentially exploited by the solver that will provide the numerical solution. And it actually turns out that if you want to keep the structure, because, again, I'm referring to the fact how quickly are we going to be able to solve the problem, how big the code for solving the problem will be, and what kind of computational operations are we going to need. So this refers to the platform complexity. And it turns out that if we keep the structure in the problem, we might get a simpler code, we might get maybe a faster solution at the expense of, say, space. Because in the sparse approach, we are keeping the states as well as the inputs as optimization variables. And at the first glance, this might sound strange, right? Because in MPC and also as formulated here, we are optimizing only over the control inputs. But nevertheless, these states are coupled to the control inputs via this prediction equation. So kind of now the question is, should we keep this prediction equation in the model, or should we eliminate it by means of some substitution? Keeping it in the optimization problem keeps the structure, so you get some kind of sparse Hessians, for instance, that might be easier to invert, at the expense of having larger problem to solve, because we have to keep not just the control inputs, but also the predicted states as optimization variables. So this would be the sparse approach. And then what many people say is, well, you know, complexity of solving a quadratic problem is basically a function of two ingredients, the number of constraints and the number of optimization variables. And usually, the fewer optimization variables we have, and also the fewer constraints, the faster we can solve the problem. At least that's the typical wisdom. So the wisdom says, try to keep the number of optimization variables low. So that's the so-called dense approach, where we apply so-called condensing to reduce or to eliminate the states from the optimization problem and only keep the control inputs as optimization variables. And I will cover both of these two. And the second one has the advantage that it has fewer variables and fewer constraints, but the overall structure is destroyed. And this keeping the structure might be important, for instance, if you are talking in the context of distributed model predictive control, where you want kind of to solve like small blocks of the overall problem and then just put them together. So in that case, you might opt for the sparse approach. If you just solve the overall problem, it might be better to use the condensed approach. So let us cover the sparse approach first. So what we aim at now is to eliminate those time indices from the optimal control problem and just basically vectorize the formulation. Okay? So what we do is that we introduce a vector of our optimization variables, and as I said, we are looking at the sparse approach where both the states and the inputs are optimization variables. So we introduce the vector of optimized states, and then each row of these matrices gives one of these constraints. So the first row here is just the initial condition, right? So it's nothing multiplied by x0, no influence of inputs. This I here is an identity matrix. And by the way, all these zeros here they are zero matrices of appropriate dimension. That's how we usually call them, with a small footnote in the textbook that the students should be able to figure out the dimensions on their own. Okay. So the first equation just corresponds to the initial condition, and all these lines here, they just represent this prediction equation for k going from 0 to n minus 1. Here in this example, I'm using the prediction horizon equal to 3. So the last k is n minus 1. So you see that x3 does not enter in the right-hand side, but it's of course a consequence of a times x2 plus b times u2. So it's just a vectorized version of these two constraints. And we can as well just abbreviate the matrices and the vectors, and then we just replace those two constraints by this compact vector notation here. Then we turn our attention to the constraints. So we might have, for instance, the input constraints. And again, our objective is to have a vectorized formulation where this time index in the optimal control problem goes from 0 to n minus 1. So then what we do is that the first constraint again describes h times u0 less than equal to hu. And here you might start noticing the very structured way the problem is formulated in. Basically, all the matrices that we end up with have this band-like structure, which makes, at least in theory, solving the problem a little bit easier, because we will see that solving quadratic programs in fact turns down to inverting some large matrices. And we know that matrix inversion in the worst and in the conventional sense, that has a complexity which is cubic in the number of, well, in the dimension of the matrix that we need to invert. The point being that if the matrix that we have to invert has this kind of special structure, then the complexity drops to something like, well, in the ideal case, n squared, n to the power of 2.5. So certainly faster than in the general case. So that's why having this structure here is so nice, at least in theory. So we do this, and by the way, at this point, let me do a first diversion to the whiteboard, because, and yeah, it kind of relates again what those constraints really are, right? So what does it mean if we write, and I believe I can wipe this already. Okay. Good. So what we encounter very often in practice are just box constraints, right? So we have just the control input is bounded by some upper bound and by some lower bound, okay? So if we want to get them into the standard inequality form, then what we do is that we convert everything to less than or equal to inequalities. So that would be this one here. It would be minus u less than or equal to the lower bound. Okay, and then we just take u out as a common. And here what we end up is the identity matrix minus the identity matrix. And here on the right-hand side, here it should be minus. We have the constant terms in the inequalities. Okay, so this would then be the matrix capital H of u, and this is the small h of u. Okay, what I want to say now is that if we do this kind of translation, and if we only have this min-max bounds, then we might as well write these kind of inequalities in a more natural form like this. Like here we have a vector of upper bounds, and here we have the vector of the lower bounds. And again, this might be kind of a more appropriate way of representing box constraints. And this might then result in some more efficient algorithms to solve the solution for the problem. For instance, those that you will try to implement on FPGAs. So what I want to say is that this description here, that's the general one, which can assume basically any type of the input constraint. So basically, if we have, say, two control inputs, say U super 1 and U super 2, then the box constraints will be just like this. So the two inputs are not correlated to each other, but we might as well have correlation, which says that if one of them is large, then the other one must be small, and so on. Okay. So these kind of red constraints, they need to be described using these matrices. If it is only about box constraints, we can as well opt for this simple representation. Okay. Anyhow, what we have just done is we have vectorized the input constraints, and we do the same for the state constraints, where this final element represents the terminal state constraint set, but the structure is still the same. So at the end of the day, we vectorized all the constraints, and we also need to vectorize the cost function, of course, but this is also similarly easy, because we just have diagonal elements that correspond to the stage cost, the terminal penalty, and the same thing for the input constraints. So we can as well vectorize the cost function as well, and then in the sparse approach, we also have to optimize the control inputs as well as the state. So that's the final type of the optimization problem that we end up with. We optimize over inputs and the states, and we have convex cost function, quadratic cost function, linear equality constraints, and linear inequality constraints. And now this fits very nicely into this overall QP structure that we aim for, right? So we define the vector of optimization variable Z as the concatenation of the vector of controls and the vector of states. We can compact this even more, so we write it like this. So we put the input penalties and the state penalties on the main diagonal. Similarly, we put these two together, again on the diagonal term, so that's the easy part. And this one, I believe, should be quite obvious where it came from. It's basically we have this equation here, but we cannot leave x on both sides, right? Because in the QP, we have to have the optimization problems on one side, and the other side only has to contain the constant terms of the problem. So the optimization variables in our problem are the x and u. So we put them on one side, and everything else we put on the other side. So doing that, say I put this x to the right-hand side. So what we end up with is we have a tilde times x minus x plus b tilde times capital U. And this part here is treated as a constant, bless you, because head x is the state estimate, so it's a constant initialization of our optimization problem, so we just put it to the left-hand side of the problem, right? Something like this. And then here we take the common, so it's a tilde minus I times x plus b tilde times u. And if we want to write it in terms of this new optimization vector, which is u and x, then the first term would be the one multiplying u, so it's b tilde, and the second one would be a tilde minus a. Okay. By the way, in theory, it should be possible to look for x by inverting this matrix, but nobody really wants to do that because the matrix is simply so huge, and there is no even a guarantee that it's invertible, because some eigenvalues might be cancelled out by this identity matrix, and then the matrix becomes singular, and we don't want to solve for x explicitly, at least not for this time being. We just keep it as an explicit relation between the states and the inputs. And voila, what we have is a standard QP for which we have algorithms to actually solve that. So this would be the dense approach where all the matrices have this band-like structure. And what is probably the most important of them being that the Hessian of the problem here has a band structure, because it's the Hessian that we have to invert at the end of the day. However, we have done this at the expense of keeping the problem fairly large, because the Hessian also accounts for the state. So yes, we can invert a banded Hessian more efficiently than a non-banded one, but it's also a much larger Hessian matrix than if we eliminate the state. So this brings us to the dense approach. And basically, the dense approach originally, I mean, it came from the fact that certain QP solving methods, they don't work that well with equality constraints. And it might also be a desire in general to eliminate equality constraints from the problem. I mean, why? Because equality constraints, they basically define affine sets, which are not fully dimensional. And then if you look like for the initial feasible point, usually we do that by maximizing the ball, which can fit into the constraints, and suddenly you cannot fit a full dimensional ball on a plane. There's all kind of practical aspects which say we better avoid equality constraints. And the other kind of the reason is that we would like to reduce the dimensionality of the problem, not to optimize over states, but only to optimize over inputs. Okay? And this is what is called condensing, and we can do condensing in general, like starting from this problem and then projecting on this equality here. That would be like the general way, which is not advised. But there is also a way which exploits the type of the problem that we are solving, and this is the optimal control problem. Because the whole idea is how to get rid of x being on both sides of this equality. We would only like to have it on one side and only let it depend on the controls over which we optimize and the initial condition. And this is exactly what the prediction model already gives us, right? It gives us a dependence of where we are now, what kind of control input we apply, versus where we end up in the subsequent time instant. So we have x1 being ax0 plus bu0, x2 ax1 plus bu1. This is the sparse approach, but now we can do this substitution, right? So for x1, we can substitute the right-hand side of this guy, and we end up with this well-known equation. Then for x3, it gets this structure. I bet you have seen this millions of times. So we end up with this general formula that relate. Okay, so what is very nice about this formula is it only has the initial state on the right-hand side, which is, again, constant in model predictive control because it comes from the state estimate. And it only depends on the control inputs that we are optimizing. Which means that if we kind of expand this general formula again in this time series, we can write the states again compactly in this vectorized formulation, but compared to the sparse approach, we no longer have this vector capital X on the right-hand side. So we have completely eliminated it, and we have that the states only depend on the initial condition and of the optimized control inputs. The price we are paying by doing so is that we have lost the structure. So the matrices are now no longer banded or sparse as they were before, but they are now lower triangular. They are very full in the sparsity sense. And this might then pose troubles because then the QP solution algorithms, they have to switch back to those general matrix inversion formulas which have this cubic complexity in how they compute the matrix inverse. Okay? But we do that to keep the number of variables low. We have this explicit relation between the control inputs, the initial condition, and the states. So that means that we can now come here, and whenever we have the state, we will just include this right-hand side. So we really do just a substitution, which eliminates the equality constraints. And whenever there was capital X in the original problem, we now get this substitution here, which means that we get rid of the equality constraints, but the Hessian here and the inequality constraints, they become a little bit more complex. Okay? And then it's again equivalent to the quadratic program. I mean, you just work the mass out, and these are the matrices which give you a one-to-one correspondence between the optimal control problem and the quadratic program in the condensed fashion. Yep.
Do you expect any problem by computing the exponent of the matrices?
Of course. Yeah, I mean, here, where was it? Here, of course, taking the case power as your prediction horizon becomes longer and longer completely destroys, say, the eigenvalues of your system matrix A. So if your system matrix contains eigenvalues that are close to 0 and you start exponentiating that, you basically start losing your dynamics down the prediction horizon. So yes, there are actually huge problems, and this might be another benefit, which, thank you for reminding me, of that sparse approach, where we don't do these kind of powers. So we let the problem decide on its own, while here we are kind of artificially in the numerical sense, destroying the problem if the numerics doesn't play well. Okay? So yeah, definitely if you have prediction horizon of 100 and you have an eigenvalue of 0.1, I mean, 0.1 to the power of 100, well, even to the power of 10 would probably be close to 0, which means you have lost your dynamics in that state, something like that. So yes.
Due to the numerical limits.
Precisely that, due to the floating point precisions, overflows, and these kind of issues. So yes, this is another factor. How much you have to worry about, or putting it other ways, how much does the sparse approach take away these kind of problems? I'm not the most qualified person to answer. Of course, there is no free lunch. So I would expect problems even in the sparse approach, but certainly fewer of them on the numerical side. But then you have problems that the overall QP problem that we need to solve becomes larger. Okay. And bottom line is, you don't have to care about all this. There are tools who do that. Okay, so there are tools to which you just provide your system, your constraints, the parameters of the cost function, and it will give you either the sparse formulation or the dense formulation. We will come back to this on the exercises. Okay? Because, 15 years ago, everybody was writing his routines just to make those huge matrices, right? And I bet every one of you, at least it was me, who was forced to do that by hand, okay? Only afterwards you realize it's just a complete waste of time and you just delegate everything to the software tools. So that's what we should do anyhow. I mean, there are more important things to focus on. Okay, so anyhow, we have two ways of formulating the quadratic programming problem, and now we come maybe to the most decisive point of this summer school, and that's how to solve those quadratic programs. And as I said, there are two approaches: the online optimization, the implicit one, and the offline optimization, the explicit one. So in the online optimization is, and by the way, I should notice that this small f on the right-hand side of the inequality constraints, that already either implicitly or explicitly accounts for the initial conditions. So whenever your state estimate changes, this right-hand side of the constraints change. And that basically means we are solving a new problem, right? All the rest can stay the same if your dynamics, if you don't change the dynamics, if you don't change the constraints, and the prediction horizon, capital H, capital F, G, and small g, they stay constant. What usually changes is the right-hand side of the constraints. So what we are going to focus now on is how to solve an optimization problem where we need to solve the problem quickly enough because the right-hand side changes, and the right-hand side accounts for the initial condition. And again, I bet that you are familiar with various ways how to solve these kind of quadratic programming problems. We can resort to exact solutions, say using the active set methods, or we can opt for inexact approaches like interior points. We can use distributed optimization like this ADMM, Aladdin, and stuff like that. But at the end of the day, if we want to solve a quadratic programming problem numerically as to optimize the primal optimizer Z, we pretty much have to perform a bunch of matrix inversions. So if we go back to embedded implementation of control, if your control architecture allows to perform matrix inversions, let alone divisions in general, because there are platforms which do not provide division as an operation, then implicit optimization is a viable option if we can do matrix inversions, because it brings many benefits, like we are able to change the parameters of the problem and so on and so forth. And this is the conventional way of solving or how to implement model predictive control on the hardware. So I'm now going to briefly focus on the active set methods. So what we do in the active set method is that we do initialization. So we pick our initial feasible optimizer Z, and we select some initial active set, right? And let me use the benefit of the whiteboard again to give some illustration. So we have the set of constraints, which would be these linear inequalities here that delimit the feasible space for the z's. So say we have two z's here. And we pick the initial condition. And since we are solving a strictly convex quadratic program, we know that we have basically three options where the optimum may lie, right? It might be that the optimum is unconstrained, which means that if we draw the level sets of the cost function, then they will be like this, okay, with the optimum being here. That's option number one, where there are no constraints active at the optimum. An constraint is active when it's satisfied with equality at the optimum, right? The second option is that the optimum will be somewhere on the boundary of this active set. So for instance, you might have a situation where the level sets are like this. So we have an optimum here. Or the optimum might be at the vertex, right? So you might have a situation here. Of course, the level set can also be completely outside. And then we are just looking for the point which is closest to the, which is on the tangent of the level set to this constraint set. But we have these three principal options. Either the optimum is unconstrained, or we have fewer constraints active than there are a number of variables, which will be scenario number 2, or there is the same number of constraints that are active as there is number of optimization variables, right? So what we do is, okay, and let me also say this. If somebody would be so kind that he would tell me which constraints are active at the optimum, we can find the optimum, meaning Z star, very efficiently, right? Because what we know is that we have a subset of those constraints that are active. So the problem that we are trying to solve, we are trying to minimize the cost function Z transpose HZ. Let's just focus on the quadratic term to keep things simpler, subject to just a subset, and I will use this capital W as the indices of the active constraints. So just keep some rows of this linear constraints and set them to a constant right-hand side, right? And the point being that if we have the same number of constraints as there are variables, there is really nothing to optimize over because the solution is exactly determined. If those constraints, moreover, are linearly independent, then this matrix here would be invertible, and then the optimal solution would be just the inversion of this set here times the right-hand side. Okay. That would be the ideal scenario, which of course would require somebody else to tell us what the active constraints are. Determining the active constraint is as difficult as solving the original problem. So we cannot really hope that somebody will just give it to us by miracle, and don't even think it's somehow easier than looking for the primal optimizer. It's exactly the other way around. We have to determine the active set because then once we know it, it's very easy to find the primal optimizer. Okay? And the whole premise of the active set method is that we do not know the optimal active set, and we try to iteratively build it step by step. Okay? And to build that, we have to start with some initial feasible Z, so the primal optimizer, and with the associated consistent active set. So if we have picked this as the initial Z, we also have to keep on or select this active set W that is consistent with this initialization, which in our case means this initialization, like W0, would be just an empty set. We cannot certainly say that let's keep this Z and let's assume constraint number 1 is active, because that's kind of inconsistent selection to the location of the initial estimate here. And I will come back to that, because determining just the feasible Z together with the kind of consistent active set is a problem on its own. But everybody just assumes let's have the initial feasible point and let's have the initial active set. And then what we do is that we do basically a Newton method. So what we try to do is we try, and let's say we are in case number 1. Okay? This is where we are now. Okay, and maybe I messed up with the subscripts and superscripts. So let's denote by Z super 0 as the iteration counter, and here sub indices would mean the components of the vector. Okay, so we are at the zeroth iteration, the initialization, and we ask ourselves, where should we move this Z0 as to improve the cost function? So obviously we would like to move ideally in one step all the way here. But you might be very well aware from the Newton methods that we usually don't go in one step to the optimum, but we consider some step length. So it might very well be that we just end up here, and then in the subsequent iterations we improve this point further, and so on and so forth. The bottom line being is that we are looking for some improving direction where the next iterate, say Z1, is equal to the previous iterate plus this direction, this improving direction, that's a vector, multiplied by some step length. So this would be the delta, and t would denote the step lengths or the multiple of this improving direction. Because of course, you don't want to end up in a situation where the improving direction brings you outside of the feasible set. This is what we must prohibit. Okay? So anyhow, what we try to look now for is that we have fixed the constraints indexed by our estimate or by our initialization. It might very well be an empty set. And we look for an improving direction which improves the quality of our previous point. So we are, yeah?
In this case, you have the active set, the correct active set already, right? Because it's the empty set. So in this case,
in this case, it would go in one iteration. Yeah, that's right. Yeah, here. But it might very well be that if the level sets are, I mean, somehow here, then we might end up overshooting where we want to end up with. Okay? Because basically what we are doing now is that we are solving, okay, if we take W as an empty set, we are solving an unconstrained problem. So we might end up all the way here, which is not what we wanted, right? We want to end up either on the edge or at the vertex. Okay? So we look for the improving direction, delta here. And here, I mean, for that, we know that we just solve the associated Karush-Tucker optimality conditions, right? So just to remind everybody, what we do here is that we take this equality constraint quadratic program, and we form the Lagrangian of this problem, right? So the Lagrangian is a function of the original optimization variables and some Lagrange multipliers. They are called lambda here. And the Lagrangian is composed of the original cost function, which in our case Z transpose HZ. I believe, yeah, I have also to include the affine term, so C transpose times Z. So that's the original cost function, and now we add the Lagrange multiplier, so it would be lambda transpose times the residual of the constraint. So it would be the FWZ minus small fw. And then we know that for this kind of problems, for the optimality, there must be stationarity conditions satisfied. So we take the gradient of the Lagrangian with respect to the optimization variables. In our case, this is just 2 times Hz. This is just C. This would be FV transpose times lambda. I believe that's it. Apparently I messed up something. This term shouldn't be there. I truly apologize. Okay, so that's the gradient with respect to the primal optimizer, and we can as well take the gradient with respect to the dual optimizer, which are the Lagrange multipliers, and these are just the residuals of the constraints. So this is just FV times Z minus FV. Okay, and then we know that what holds at optimality, so truth to be speaking, or to be correct, we put the stars here because stationarity holds at the optimum. So we have 2 equations in 2 unknowns. So the unknowns are the primal optimizer and the Lagrange multipliers. And then what we do is that since both of these 2 equalities, they are linear in those decision variables, we can as well take the common. So we take Z star and lambda star here. We pre-multiply it by 2H. Here it's just FV transpose. Here from this equation is just FW. It's a 0 matrix here, and that should be equal to everything what is constant and goes to the right-hand side, which means basically minus C and 0 here. And then searching for the primal and for the dual optimizer now means inverting this matrix. So that's why I was talking so much about matrix inversions before. It turns out that to find the improving direction, we have to invert the matrix. And hopefully, well, the matrix will be invertible provided the Hessian is invertible, which that's why we had those technical assumptions about positive definiteness of the cost function. And the constraints here have to be linearly independent. Under these two conditions, we can find the improving direction, delta. And now we look at the properties of the primal optimizer. So now we are solving it with respect to delta. So now delta is the primal optimizer and lambda is the dual optimizer. Okay? What we also know for this equality constraint QP is that the dual optimizer lambda can be anything. It can be 0, it can be positive, it can be negative. But if we consider the original problem with inequalities, then we do know that the Lagrange multipliers must be non-negative, right? So now we check whether by solving a different problem, an equality constraint QP, we didn't by chance found a solution which is also optimal for the original problem. And for that, we check what the improving direction is. If the improving direction is 0, it might mean that we are already at the optimum, but we don't know until we look at the associated dual optimizer. If by chance all of them are non-negative, we have a certificate that the z we have initialized the problem with is also the global optimum of our original inequality-based problem. Because there is no improvement we can make, and we have a certificate that z is also optimal. So this is the best case. That's kind of the convergence of the active set method. This is what we obtain at the end of the algorithm. To get there, it might take a road. It might take a couple of iterations. So usually we are not that lucky. So either delta is not 0 or some of these lambdas are negative. Okay? What does it mean that some of these lambdas are negative? That means that we have restricted our solution too much. Say the solution is here in case number 2, but somehow we have selected, or from the previous iteration, this was the estimate of the optimal solution. Of course, we could improve, but by forcing ourselves to satisfy this constraint with equality, we can move only along this line. That improving direction will have to be parallel with this constraint. That means the best we could do is to get to this vertex, which is still away from the optimum. That means that there is a constraint which keeps us in place, which is not optimal for the original problem. And we can recognize that by looking at which lambdas, which of these dual variables are negative. Because again, for the inequality constraint formulation, they had to be non-negative. So if there is an element in your lambda vector that is negative, we remove one constraint. Which constraint to remove if there are many of them indicated to be removed? Well, this is where a clever heuristics come into play. We remove the one which is kind of the worst from the Lagrangian sense, meaning the one which is the most negative one. And these are heuristics. I mean, you could as well remove any of them or remove the one closest to 0. But it turns out that there are many of these little heuristic kind of rules which make the procedure converge extremely efficiently. And I will show you what the possible worst case might be, and it's just mind exploding. So if there is something which keeps us from, or prevents us from improving, and if it is a constraint which prevents us from improving, let's get rid of one of those constraints. Another type of heuristics would be to remove plenty of constraints at the same time. It turns out doing it one at a time is better than doing something in one shot. So there is no improvement, which by the way would mean that we are, okay, I was wrong here. I should have drawn the point at the very vertex, right? So I would ideally like to move perpendicular, but kind of the constraint doesn't allow me to move perpendicularly. Okay? So that's why delta is 0. But some lambda is negative. So we will get rid of the constraint. So at the next iteration, if there was something in this constraint set, we will just remove one of those constraints. And we repeat again. So again, we solve this equality constraint QP by using this. Now these matrices here, they change. Oh, by the way, I'm sorry again. It should be FW here as well, but these are just little details. So that would be one case, how to update the active set. The other update of the active set would be that we have found an improving direction. Okay? It might very well be this case, as it was originally. So say this was our improving direction now. This was the delta that we have found. Of course, in the convex case, yes, we would end up all the way here, but just for the sake of the argument, say this was the improving direction. So what we do next is we check whether by moving all the way by the improving direction, we are still within of constraints. So we check whether this new point that we would find, this z1, which is e0 plus delta, where the step size is equal to 1, whether it still satisfies constraints. If it satisfies constraints, fine, we will just use the same z as the initialization of the next iteration. However, what can also happen is exactly the case which was drawn here, that the improving direction brings us outside of the constraints. Then what we do in such a situation is, by, again, fancy math, we determine which of the constraints did we violate first. Because this point here, it violates not just this constraint, but it as well violates this constraint, because these constraints are hyperplanes. They are not line segments. They spread all the way to plus and minus infinity. So in fact, by going in this direction, we as well, so if I number the constraints, this would be 1, 2, 3, 4, and 5. Obviously, we violate constraint number 5, but we as well violate constraint number 4. Okay? Probably none of the others, since they go outside of the of this direction. But again, we have at least two options of like asking ourselves, which constraint should we take the most care of? And we do that by actually determining which of the constraints will be hit first by moving in this improving delta direction. And that's just a fancy formula which will give you basically the distances between these 2 points and the constraints. And then we simply include to our active set the constraint which is closest on our way from the initial point all the way to the improving direction. So again, it's just a heuristic. We could have added the furthest constraint away, but I guess it's quite a common sense to include the constraint which we will hit first anyhow. Okay? And this is what constitutes one iteration of the active set method. So just to recap, what we do is we start with some initial point, then we try to improve the point, and we look whether there is something which prevents us from improving. What can prevent us is that there is a constraint which holds us in place, then we get rid of the constraint. Or there is improvement, but we have to be careful as not to overshoot the constraints, in which case we add a constraint to the active set. And then the procedure kind of iterates, adding and removing one constraint at a time, and potentially we will end up with a solution. How many iterations it will take? Well, the worst case is absolutely non-acceptable. In the worst case, we have to explore all possible combinations of active constraints, which basically means that if we have, say, 5 constraints and 2 variables, how many options do we have? Well, no constraints could be active at the optimum, right? Or a single constraint can be active at the optimum, case number 2. How many options do we have here? Well, 5, right? Or 2 constraints could be active at the optimum. How options do we have? Well, 1, 2, 1, 3, you get the idea, it's 5 over 2, right? So if you would have 3 optimization variables, it would be 5 over 3, right? What's the upper limit? Well, it's when you have as many constraints active at the optimum as you have the number of variables. So then it gives this formula here. So this is just summation of combinatorial expressions. And just for tiny little problems, like 5 variables and 60 constraints, and this is really like take prediction horizon 5, system with 1 input and 2 states, tiny little problem. There are 100 billion possible combinations of constraints that can possibly be active. Of course, not all of them might even be feasible. Okay? For instance, it is certainly infeasible to have simultaneously constraint number 1 and constraint number 3 active, right? Inside of that constraint set. But the active set method somehow needs to figure this out by, again, solving this problem and looking that this matrix here is of like rank deficient and cannot be inverted and these kind of things. So in the worst case, these are, I mean, huge number of iterations, but because of that clever heuristics, this really cuts the number of iterations down tremendously. And for most practical problems, these active set methods, they converge extremely quickly, say less than 100 iterations, and sometimes it's even far less than that. Okay? However, the implementation requires matrix inversions. So if we are going to do this on FPGAs or Arduinos, we are fine. If you want to do it on programmable logic controllers, as I will do afterwards, that's a big no-no, okay? Because we simply cannot do matrix inversions, and then we must do something else. And the last pesky point about this scheme, which again, pretty much everybody neglects, like everybody's aware of that, but doesn't want to tell the inconvenient truth. And the inconvenient truth is that finding this initial point is difficult. I mean, yes, we do it in the context of model predictive control. So you might say, oh, I will just take the solution from the previous time step. But you might be now in a complete different active set. Or, well, the optimizer estimate will not be consistent with the estimate of your active set. So what we do then is, in fact, we have to solve a different variant of this problem, again by an active set method, where we basically relax the constraints. We soften the right-hand side of the constraints by including some slack variables. Bottom line being, we have to solve two of these problems at each time step of the MPC implementation. One to find the initial point for the actual optimization. And this, again, we have to factor in when we are deciding whether we have hardware that is capable enough of solving our problems. So these are these little tiny details that we have to be aware about when it comes to practical implementation.